change, the night sky has come to signify all that is eternal. Seasons may pass. Civilizations may rise and fall. But the stars still traverse the heavens each night in a timeless celestial procession. So steady is the light of the stars that the constellations we see each night are the same ones our ancestors gazed upon thousands of years ago. And each individual star could shine for millions or billions of years more. The stars and galaxies convey the impression that the things we see in the universe are permanent and unchanging, at least over the course of a human lifetime. But that's not always the case. One of the most astonishing phenomena in the night sky is so fleeting that most people have never seen it, even though it's very common and can easily be found without a telescope. For generations, the aurora borealis, or northern lights, have enchanted those lucky enough to see them. With their bright colors and strange, wavering movements, the auroras seem to be alive with a supernatural energy, a perception that arises again and again in stories from the past. In North America, for example, the Algonquin people explained them as the light reflected from the campfire of the Creator. While to the Vikings of Scandinavia, they were the Valkyrie, supernatural beings who accompanied fallen warriors on their way to meet the gods. And in many northern cultures, they are simply regarded as the spirits of the ancestors, dancing in the sky. But it was the astronomer Galileo in the 1600s who first named these events aurora, after the Roman goddess of the dawn. Galileo incorrectly speculated that auroras were reflections of the sun's rays. But he did get one thing right. It is the sun that is ultimately responsible for the aurora. It would take 3 more centuries before Christian Birkeland, a Norwegian scientist, hit upon the correct explanation. The aurora, it turns out, are the result of billions of microscopic mid-air collisions. Starting at around 250 kilometers above Earth's surface, electrically charged particles from the sun collide with the oxygen and nitrogen atoms and molecules in our atmosphere. The gases are energized by these collisions, giving off a colorful glow. The different colors relate to the height, energy level, and type of gas. For example, oxygen can glow both red and green, while energized nitrogen can produce a blue or crimson color, or sometimes both at once, which makes the aurora seem purple. The solar particles responsible for all this energizing can be seen most vividly during a solar eclipse. As the moon slips in front of the sun, the blazing light of the sun's surface is temporarily blocked. As the sky goes dark, a feathery glow appears around the silhouette of the moon. This is the solar corona, a region heated to extreme temperatures and eventually driven outward into space. As they travel, the solar particles form an invisible current called the solar wind, which blows past the planets of our solar system on its way to the stars. As the solar wind flows past Earth, some of the particles are captured by our planet's magnetic field, which is generated deep inside Earth's core. Like tiny compass needles, they follow the lines of magnetic force heading down to our planet. The magnetic field lines converge near the north and south poles. The aurora they produce are mostly seen far from the equator, closer to the Arctic and Antarctic regions of our planet. Sometimes auroras are dazzling and brilliant, and other times they do not appear at all. The secret to why auroras are sometimes spectacular and sometimes scarce lies again with the sun. The more active the sun, the more potent the solar wind, and the more beautiful the auroras. Like Earth, the sun has its own magnetic field, but the sun's is more powerful and it originates within the hot plasma deep in the interior. The most obvious signs of the sun's magnetism are sunspots, dark patches that appear where lines of magnetic force have broken through the surface. Regions associated with sunspots can be incredibly dynamic, sometimes spawning massive explosions called solar flares, which can release more energy than the detonation of 1 million nuclear bombs. An active sun is also more prone to coronal mass ejections, magnetized bubbles that can grow within the sun's corona and ultimately burst outward, sending billions of tons of energized particles racing through space, turning the steady flow of the solar wind into the equivalent of a hurricane. If such an event happens, within hours, high-speed particles are battering Earth's magnetic field. Down on the ground, the effect is often a spectacular display of aurora. But there are other effects. Violent fluctuations in the Earth's magnetic field can overload power lines and cause blackouts. Because of their potential to disrupt technology on Earth, solar storms are the subject of intense study. That means the aurora have now stepped out of myth and legend to become part of a larger space laboratory, helping us to understand the sun and its influence on our planet. The aurora may be a phenomenon of our atmosphere, but it is directly connected to forces at work far off in outer space. Perhaps it's fitting, then, that we have to go to space to understand it best. Like a delicate sculpture suspended in silent grace, the International Space Station sails over our planet. The station is humanity's most ambitious outpost. It lies only a few hundred kilometers above Earth's surface, yet it is our beachhead into the infinite vastness beyond. With the station, we now have a perpetual eye on our planet from above, a way to see Earth in all its glory, including oceans, continents, and our best views yet of the Earth's colorful aurora. Until the arrival of spaceflight, we really had only one place from which to view the aurora, down on the ground. That's changed now, and so has our understanding of what's really going on when the sky is on fire with northern lights. When it comes to the aurora, it turns out that space is the place to get the big picture.
4, 3, 2, 1.
In 2007, NASA's Vistas mission probed the forces that can turn a calm aurora at the poles into an all-sky light show with potentially paralyzing consequences for our technology. 5 microsatellites measured electric and magnetic fields in space, as well as the flow of solar particles during an aurora. At the same time, an array of 20 ground-based stations in Canada and Alaska took wide-angle shots of the aurora while making magnetic measurements. Themis revealed that the energy contained in just one solar storm is equivalent to that released in a powerful earthquake. The mission also found invisible strands of Earth's magnetic field dangling 40,000 kilometers out into space. Called magnetic ropes, these ephemeral fields capture solar wind particles, briefly tying the Sun and Earth together until the ropes unwind and dissipate. A parallel project, Europe's cluster mission, involves 4 identical satellites orbiting the planet in formation. Their goal is to provide a 3-dimensional picture of how the solar wind interacts with the Earth's magnetic field and produces aurora. Like mapping an electromagnetic landscape, Cluster is helping determine exactly how particles that originate at the Sun gradually find their way down into our atmosphere. These studies from space remind us that auroras are a planet-wide phenomenon, and they should arise wherever the same 3 ingredients occur anywhere in our solar system. Those ingredients include the flow of particles from the solar wind, a planet with a strong magnetic field, and a dense atmosphere for the solar particles to collide with. The planet with the strongest magnetic field in our solar system is Jupiter. A giant ball of gas so large all of the other planets would fit inside it. Jupiter would seem like a prime spot to search for auroras beyond Earth. Even at a distance 5 times farther from the Sun than Earth, Jupiter's intense magnetic field is strong enough to pull in the solar wind. Io, the closest closest of Jupiter's large moons sports its own magnetic field. Gas in its atmosphere glows, causing a small aurora of its own. This field affects particles caught in Jupiter's magnetic web, funneling them toward a specific spot in the giant planet's atmosphere, creating a bright spot in the aurora that changes position with Io. Fainter spots in Jupiter's auroras are believed to be the footprints of Ganymede and Europa, two more of Jupiter's large moons. Saturn is another gas giant in the solar system with auroras. First captured in one of the Hubble Space Telescope's early images, these auroras are now monitored by the Cassini spacecraft currently orbiting Saturn. Hubble and Cassini both found auroral ovals around Saturn's poles, but glowing in ultraviolet light. Later, Cassini found a whole new set of auroras glowing in infrared. This aurora, unlike any other before seen, covers the pole rather than crowning it like a glowing ring. The ability to explore the other planets in our solar system has shown us that auroras are not a phenomenon unique to Earth. Anywhere where a moon or planet with a gaseous atmosphere and a strong magnetic field is exposed to the relentless tides of the solar wind, we should expect to see something like the Northern Lights. And now, with technology on our side, it's possible to enjoy these dancing lights as never before. Have inspired our stories and filled our dreams since long before the beginning of recorded history. Yet our efforts to adequately record and study these colorful moving lights in all their ethereal beauty have always fallen short. Until now. Today, the advent of digital photography makes it possible to capture the faint and ever-changing light from the auroras. Now, backyard stargazers around the world are putting these tools to use and showing us what until now only a few were lucky enough to witness. An aurora we see from the ground is part of a larger structure in the form of two large ovals centered on the north and south magnetic poles. To see auroras regularly, you have to be under one of these auroral ovals, or at least close enough to catch a glimpse. That means people living in the far north or south have the best chance to see auroras on a regular basis. When there are more particles flowing toward observers at latitudes closer to the equator will only see the highest auroras, which appear as a reddish glow in the direction of the poles. In some cases, auroras hang like curtains above the Earth. This is because Earth's magnetic field traps particles from the solar wind and channels them almost straight down. They cannot wander away from the field lines, so from a distance we see them as sheets of light. Some of the most spectacular auroras of all are those that occur when these shifting curtains of light are directly overhead. They create the effect of radiating lines of moving light, pulsing and emanating from a central point. Such displays are breathtaking, and they ensure that no matter how well we come to understand auroras, we will never cease to be filled with wonder when we see them. When you stop and think about it, no other process in nature so directly connects something that's happening deep beneath our feet in the core of the planet with something that's happening inside a star, our sun. But there's also another way that the aurora may connect us here on Earth to the larger universe that we're a part of. Because they are a product of Earth's magnetic field, auroras are a visible sign our planet is largely protected from the bombardment of particle radiation that would otherwise be raining down on us from space. By deflecting and channeling many of these particles toward the north and south poles, the magnetic field acts as a shield, making the Earth's surface safe for life as we know it. Although today we are far from being able to observe other Earths directly, astronomers are now beginning to test the idea that we might someday be able to detect the energy of an auroral display underway on another world beyond our solar system. If such a detection could be made, it would come with some big implications. It would allow us to distinguish between a planet like Earth and similarly sized planets like Venus, which has no magnetic field and is completely inhospitable. In fact, the presence of auroras on another planet would be our cue to look for signs of life. Mysterious and beautiful, intriguingly complex, we have now come to realize that the auroras that light up our night sky are also a colorful calling card that advertises our existence. Perhaps the auroras of another world will one day help lead us to our first meaningful contact with other conscious beings in the universe, and point the way to a cosmos full of light and life.